Now that we've got the concept of limits under our belt, the next natural progression from that is to talk about the derivative because we know the derivative is defined in terms of a limit. So just to refresh you from Calc 1, remember if you were to take the derivative of a single variable function, it was the limit as h went to 0 of f of x plus h minus f of x all over h. Okay. What we want to do is we want to come up with an equivalent expression, but now if I have a function of two variables. And in the process of this, we have this normal derivative, but because of us having a multivariable function, it's a concept called a partial derivative. So instead, we're partially differentiating it with respect to one of the variables. That's that input. So that's where the name comes from. So we're going to let f of xy be a function of two variables. So let's start by fixing the y value. If we fix one variable, say we let y equal some constant b. Okay, then x can run freely, but y is fixed to be this particular value. Then the function where we replace y by b is now a single variable function. X is the only thing that changes. Y is fixed to be a constant. So because of that, we're going to call this g of x. It is only dependent upon x now because y is fixed. So this single variable function, if it has a derivative, then it's considered to be a partial derivative of f with respect to x at a particular value. And then again, of course, we can generalize it to just be a partial derivative, not just at a specific point. But ultimately, if g has a derivative, this single variable function, at say x equals a, then we define the partial derivative of f with respect to x at the point AB as follows. To indicate that it's a derivative with respect to x, we can use a subscript of x. This is evaluated at the point AB. It is just how we would normally differentiate the function, because again, remember, we've replaced y by a constant, so x is the only variable. So you differentiate this as you normally would, where g of x is again a single variable function. But again, realistically, we don't want to just do this for every specific point. We want to come up with a function that represents a partial derivative. And all you're going to do in that case is you treat y like a constant and then apply that derivative to anything dealing with x. So formally, by definition, we have the partial derivative of f with respect to x is the following. So in general, this function is given by a limit, and it is still the same kind of limit. It's the limit as h approaches 0. You would have f of x plus h, and then you would have minus f of x But since you have that second component, you just leave y as is. So everything is in the x component. So this is the formal definition, of course, provided this limit exists. Okay. And then in the same way, you could do the exact opposite. You can consider x to be the thing that's constant and instead apply this change to the y component. And that would be the partial derivative of f with respect to y. So in the same manner, the partial derivative of f with respect to y is the following. To indicate y, we use a subscript of y, and it would be the same limit, but now we're going to apply that in the y component. So it's f of y plus h minus f of y all over h. And that first component dealing with x stays the same. Again, provided this limit exists. Okay. So essentially, finding partial derivatives is not going to be much different for you. You've got a function with two things. If I want to take the derivative with respect to x, all I'm going to do is differentiate the x components as normal. You treat anything with y like a constant. And then vice versa, if you want to take the derivative with respect to y, your x is treated just like a constant attached to that variable. And then all of your normal differentiation rules apply. So to kind of summarize that, essentially, to find partial derivatives, we fix one variable and take a derivative with respect to the other. Now, if you remember, the reason we went through derivatives back in Calc 1 was we were concerned with that tangent line problem. So we were trying to find the slope of the line tangent. But the only issue was you knew a single point. So when we think about these partial derivatives, because we're working in surfaces, these partials still give us that same kind of information. They're representing slopes of tangent lines, but they're just in specific directions. So just to give you a visual of that, geometrically, these partial derivatives still represent slopes of tangent lines. So let's draw a nice little picture in 3D. Our x, our y, and our z. So suppose we have this surface. Maybe it looks something like this. Here is what our multivariable function would plot out to. If I'm looking at a specific value p, if I draw that projection down here to the xy plane, this has coordinates a, b, 0. Okay. What you're looking at is if I kind of just draw the trace of this thing parallel to the x-axis and then parallel to the y-axis. So basically imagine like you have a coordinate plane sitting on there. It's a projection of that graph onto the y-axis and x-axis. This first line which runs parallel to the x-axis. I'll call that line 1. That one is going to have a slope, which is the partial derivative of x evaluated at AB. Okay, it has no z, or it has no y component, and then same thing, it's running parallel to the x-axis, so it also has no z component. So it is giving you just directly that slope, because remember, technically you needed a full direction, but it's just in the x direction. So the y and z components are 0 of that. And then likewise, if I look at line 2, that's one that's going to run parallel to the y-axis. So that was not a good picture of it, but I didn't draw a great transfer or a great projection here. So this is kind of running parallel. So this line would run parallel to the y-axis. We'll call that line 2. Okay. That is going to have slope, which is the partial derivative of f with respect to y evaluated at that point. And again, it's not moving in the z direction, it's not moving in the x direction at all, it is solely just that component. So you can come up with the actual equations of these lines based on the stuff we did in an earlier chapter. Okay? So line 1 and line 2 are tangent to the surface C, which is a multivariable function of x and y, at the point P. The coordinates of P here are A, B, and then whatever the z value is corresponding to it, which is just the function evaluated at that point. The slope of line 1 is the partial of the function with respect to x, evaluated at the point AB, while the slope of line 2 is the partial with respect to y, evaluated at the point AB. Okay? So what you did in Calc 1 to find the equation of a tangent line to a curve, you took the derivative, you plugged in that x value, that went ahead and it gave you the slope, and then you had the point, you would just use your point slope form to come up with the tangent line. Same idea here, we have the point because we know the xy value, we can find the z value by plugging it in. But because we're in 3 dimensions, if you want the equation of the tangent line, you need the direction that tangent line is heading, and then you also need the slope in each direction. But again, it's not moving in this case, line 2, it's not moving in the x or z, so those slopes are 0. So the y slope is just going to be whatever that partial is with respect to y at that point. So same geometric interpretation. Okay. And then in the same manner that we would call our derivatives rates of changes, so the rate of change of f or the rate of change of y with respect to x, same exact thing here. They're still representing rates of change. So partial derivatives still represent rates of change. Basically meaning that the partial with respect to x represents the rate of change of z with respect to x. Okay. Big partial derivative at that particular point is then telling you that your slope is increasing greatly in that direction. In a very soon section, we'll also talk about how do I find slopes in other directions besides this, and those are called our directional derivatives. Okay. So pretty much most of the section is just calculating a ton of partial derivatives and calculating second derivatives and things of that nature. So you'll get a ton of examples really soon, but the last thing I want to go over is the notation for this. Because if you remember, we had a bunch of different ways to represent single variable derivatives. So I'll refresh on those just so you have it. If you had y was a function of x, then there was a couple things we could do to indicate the derivative. You could write y prime. You could write f prime. You could write the derivative of y with respect to x. Okay? These were all of our methods to indicate the derivative. Now, when we're talking about partials, we have still analogous notation, and then a couple extra ones that we use here. So these derivatives are representing a full derivative because there's just that single variable dependence. And same thing, this prime notation is solely used when we have single variable dependence. This particular notation, remember, is called Leibniz notation. So instead, if I have something that has multivariable dependence, then I'm not going to use a straight d over dx, okay? This is solely single variable. So really emphasizing that is single variable dependence, okay? Our notation for partials has to indicate that there is multivariable dependence. So here, if z is a function of x and y, then we have a couple different things. To indicate that I want to take the partial of f with respect to x, you can drop that input. You can just say f sub x. And I can still use this operator like we have up here. This is d over dx of y. But instead of using that d to indicate it's a partial, we use this operator. So this indicates take the partial with respect to x of this particular function. And in the same way we have Leibniz notation, you can say the partial of f with respect to x. Okay. Other things you can do, these ones aren't as commonly used. These first couple are going to be our main ones. You can also use a 1 as a subscript because this is x, it's the first component. You can use a capital D to say differentiate with respect to x of f, or differentiate with respect to the first variable. And so likewise, if I want to indicate the partial with respect to y, you can just write f sub y. Your operator would be the partial with respect to y of f of xy, or in that nicer Leibniz notation, partial of f with respect to y. Since this is the second variable, you can use a 2 as a subscript, or you can use d sub y of f, or d2 of f. Okay. And then in the same manner too, like you have y prime, you can also say z with respect to x, or z with respect to y. Those ones are just less common with these partial derivatives. We usually like to use f sub x, f sub y. Okay. All right, so now that we got all the notation and everything out of the way, let's try some examples. Let's find the first partials, f sub x and f sub y, for the following functions. And the first example we're going to look at is the function, which is x to the fourth plus 8x squared y plus 5. While we're starting out, I'm going to do way more steps than you actually need to, but just so you can kind of follow along and get a grasp of these things. But the more you do this, the less work you have to show, just like in Calc 1. You didn't need to do every single step to show chain rule and things of that nature. But all of your standard differentiation techniques apply. So let's start with the partial with respect to x. I need to take the derivative of each of these things with respect to the variable x. It's like this is not a step you need to show in. I'm going to take the partial with respect to x of the first piece, the partial with respect to x of the second, and the partial with respect to x of the third. Okay. First one's hopefully pretty easy. If you're differentiating x to the fourth with respect to x, well, that's just 4x cubed. Derivative of x to the fourth is just your power rule. In this next piece, when I'm differentiating 8x squared y with respect to x, the 8 is obviously a constant, but you're going to treat the y as a constant as well, because the variable I'm considering is x. So remember, your constants just stay attached. So you can technically pop those right out, and instead you're going to take the partial with respect to x of x squared. And then the last piece, if I'm differentiating a constant, derivative of that is 0. Okay. So I've got one last step then. If I take the derivative with respect to x of x squared, that is going to be 2x. So ultimately, the partial with respect to x is 4x cubed plus 16xy. Okay. Now, realistically, you can really just jump like right to this step. You don't need all that stuff in between, but just to show you how we go about this process. If I'm differentiating this with respect to x, derivative of x squared is 2x. So I just bring that down and I keep the 8 and the y attached to it. So I'll show you with this next one when we do the partial with respect to y without as many steps. So all I'm going to do is differentiate each piece with respect to y. And for the first one, if I'm differentiating x to the fourth with respect to y, x to the fourth is just a constant. So that one is 0. For the second piece, if I'm differentiating y, its derivative is 1. So I'm just getting the constant attached to it. So you get 8x squared. And then the derivative of 5 with respect to y is also 0. So ultimately, the partial with respect to y is 8x squared. Okay. So hopefully not too bad in practice. Again, you really just get to jump down to this step, but to show you piece by piece where everything comes from. We can make it more complicated, and we can still apply our chain rule in here. So let's try this next one. Our function is going to be tangent of xy. So if I take the partial with respect to x, that is that inside piece, so I've got to use my chain rule. I had to go outside in, so derivative of tangent is secant squared. It stays evaluated at the inside. And now my chain rule is telling me I've got to take the derivative of this thing. So we've got to take the derivative with respect to x of xy. So that gives me secant squared of xy. And then the derivative of xy with respect to x is just going to be y. Because the derivative of this is 1, so I get the constant attached to it. And that is my first partial with respect to x. If I take the partial with respect to y, it's honestly going to be the same thing, just I have a different partial at the end to take. So going outside in, derivative of tangent is secant squared, stays evaluated at xy, and then we've got to take the partial with respect to y of the inside from chain rule again. And then in this case, when I differentiate with respect to y, derivative of y is 1, so I just get the constant attached to it. So an x pops out. Okay. So that is how we find first derivatives. But just like we could find second and third and fourth derivatives, you can do exactly the same thing here. But it does get a little bit messy with these, especially because of the ordering. So the subscript, the order is going to matter, okay? So I'm going to kind of summarize everything and then also talk about just more notations with that for higher order derivatives. And then again, we'll do lots of examples. So if f of xy is a function of two variables, then the partial with respect to x and the partial with respect to y are also functions of two variables. And you can see that easily right here. Function of two variables, function of two variables. Even in the case that it's not, like here, this is technically just a function of x in the end. It does not matter. I can still take the partial of that with respect to y. Okay. So we can keep going and we can take more derivatives. So ultimately, we can take the derivatives. I've got the partial with respect to x. I now want to differentiate that again with respect to x. But I also could take the partial with respect to x and differentiate it with respect to y. Then we've got f sub y. Well, I can differentiate that with respect to each variable as well. Okay. So my first derivatives, I have two of them for two variables. For my second derivatives, I have 4. So these 4 are called the second partial derivatives. Okay. And we can use any of the following notations. So if I start with f sub x, and then I differentiate it with respect to x. So I'm differentiating with respect to x twice. The easier way to write this is you just use 2 x's. Or you can use 1, 1 because it is that first component. The other thing we're doing is we were working with the partial with respect to x. I'm now taking the partial of that with respect to x again. So if you remember Leibniz notation to say take two derivatives of f with respect to x twice. Analogous thing here, you take two partials of f and you're doing that with respect to x twice. Okay. And then of course, you can change the f to z. This is where it gets a little bit hard when I have mixed partials. The order is going to be different depending on the notation. So if I'm looking at this order, I'm going to write that as xy. So this one you work just chronologically as you read it. This means x first, then y. And same thing, you would write 1, 2. So the first one and then the second one. Leibniz notation is one that's going to be backwards because here you started with the partial with respect to f of x, partial of f with respect to x, and then I'm now taking the partial with respect to y. So I'm still taking two derivatives partially of f, but you see here the order is going to be backwards. So this indication you worked outside in, this one is still meaning x first, then y. And then in terms of z, you just change it to z. Okay. Now maybe you're asking yourself, well, is this going to be any different than if I switch the order? If I take a derivative with respect to y and then x? And if you're starting with a function and finding derivatives, no, they should be exactly the same. That idea, however, is going to be important for us. We want the mixed partials to be the same. If it's a nice function, that will happen. So if I go to find this one instead, I start with differentiating with respect to y and then x. The notation here would be yx, again, y first, then x, or starting with differentiating with respect to the second variable and then the first. And so here we started with the partial with respect to y, and then we were finding the partial with respect to x. So we're taking two derivatives of f, first with respect to y, then with respect to x, or instead doing z. And so again, you're going to hope these are the same. If it's a nice function, it should be. And again, for us, when we're finding second derivatives, that should always be the case. If you don't get that, you probably made a small error somewhere in here. And then for our last one, I can take the partial with respect to y twice. This one is nice because you don't have to worry about the order. It is the same variable. So we're taking the partial with respect to y of the partial of f with respect to y. So two partial derivatives, both of them with respect to y. And then you could change that to z because z is the same thing as y, or as f. Okay? So let's try some examples. We're going to find the second partial derivatives. And to be able to find the second partial derivatives, you've got to find the first anyway. So we'll get more practice with that. So we'll start somewhat nice. Let's do x cubed y to the 5th plus 2x to the 4th y. So I'm going to start with the partial with respect to x. And here's where I'll start skipping, just like you're probably going to do in your work. When I differentiate this with respect to x, again, the y to the 5th stays constant, so I just differentiate x cubed. Derivative of that is 3x squared, and the y to the 5th stays attached. Keeps changing my tool on me. There we go. Now when I go to differentiate this, I'm just differentiating x to the 4th. The 2 and the y stay attached. So I bring the 4 down and I decrease the power by 1. So this will give me 8x cubed y. You can find your second partials from here. Now I can differentiate this with respect to x again. And so same process, I'm just differentiating x squared. That derivative is 2x. The 3 and the y to the 5th stay attached. So this gives me 6x times y to the 5th. Derivative of x cubed, the 3 comes down, so it would be 24. Decrease the power by 1. That gives me 24x squared y. So that is one of my second partials. Now I'll do the other one as well. We've got the partial with respect to x. Let's differentiate it with respect to y now. So these stay constant. Derivative of y to the 5th, we bring the 5 down. So that will be 15. X squared stays attached. And then we get y to the 4th. And my tool, there we go. Now for the next one, when I differentiate y, that's just 1. So you just get the 8x cubed attached to it. So that becomes 8x cubed. And so that is our second partial. And this one we call our second mixed partial. Now I need to do the same thing, but I need to start with the partial with respect to y. So beginning back with my original function, differentiating this would be 5y to the 4th. So the first component is 5, the x cubed stays, and then we get y to the 4th. Derivative of this is 1, so we just get 2x to the 4th. Now let's go ahead and differentiate this with respect to x. So again, just differentiating these two pieces. So the partial of y with then respect to x again. Derivative of x cubed is 3x squared. So bringing the 3 down gives me 15x squared y to the 4th. And then the derivative of 2x to the 4th is 8x cubed. And so you'll notice here, these two are the same thing, which is nice. That is what I should get in this example because I'm finding derivatives. Okay. This is actually something I'll say in a second, but this is actually called Clairaut's theorem. So if these partials that we get are continuous on some disk or domain, then they better equal each other. Now I got one more partial to find, which is taking a derivative with respect to y twice. So here, just need to differentiate y to the 4th. So bringing the 4 down gives me 20 x cubed y cubed, and then the derivative of 2x to the 4th with respect to y is nothing because that is just a constant. So these are the second partial derivatives for this function. So hopefully that one wasn't too bad. This next one, not going to be as nice, unfortunately. So I'm going to call this function u now of xy. It is e to the xy times sine of y. So not going to be pretty. Going to be some messy stuff going on. Okay. Ultimately, you should be able to leave these things kind of expanded out. You don't have to necessarily group all of the pieces or factor out stuff in common. I do, however, want to show that mixed partials are the same in this case. So I will for those instances. But again, in terms of like a test or something like that, no, you don't have to necessarily like group everything together super nicely because we're not going to keep going after these second derivatives for these examples. So let's try this one out. Let's start by the partial with respect to x. So thankfully, only this deals with x. Sine of y is treated like a constant. So when I take my derivative, I'm going to keep the sine of y out front because it's treated like a constant. Derivative of e to the anything is e to the anything. But then chain rule, I've got to take the derivative of that thing. Okay. So going through that, this gives us sine of y times e to the xy. The derivative with respect to x here is going to be y. Okay. So not pretty, but that's okay. Now let's go ahead and let's find the partial with respect to x again. So these are both constants. This is the only thing that's dealing with x. So I'm even going to rewrite this just to kind of keep those together. We've got y, sine of y, and then e to the xy. So the y times sine of y stays out front. Derivative of e to the xy is e to the xy. And then chain rule again, I've got to take the derivative with respect to x of xy. Okay. So ultimately that just gives me another y. So you can group it if you want as y squared out front. If you left it like this as is, that's not a problem either. So you can see if I tried to take third derivatives, it would not be pretty because you have a lot of y's going on here. So second derivative as far as we're going to go for this particular problem. If I'm asking you for higher partials, it'll be with nicer functions. Okay. But now let's try to find the other partial of this, now with respect to y. Okay. And this is where it gets kind of messy because we have three things that deal with y. So maybe you learned if you had like a triple product rule. It's not something that's typically taught because it's a messy formula that you don't need. Instead, what I'm going to do is I'm going to group these, treat this as one function, this is one function. It's just going to be when I go to take this derivative, I'm going to have to apply product rule a second time. Okay. So thinking back to our product rule, we keep the first, which I'm calling y sine of y. And then I need to differentiate the second. So I'm taking the derivative with respect to y of e to the xy. And then I'm going to differentiate the first. And I'm going to keep the second. Okay. So this is the first, this is the second. keep the first, derivative of the second, derivative of the first, keep the second. Just my general product rule. And now from here, I can dissect it down. So that's y sine of y. And now when I take the derivative of e to the xy with respect to y, you still get the same thing back. And then chain rule, I've got to take the derivative with respect to y of the exponent. And now here, I need to apply product rule. So I've got two separate functions. I've got y, and then I've got sine of y. So going through my product rule, I keep the first, and then I'm going to have to take the derivative of the second. And then I add derivative of the first times the second. So we're getting there. Not pretty, but we're getting there. This gives us y sine of y, e to the xy, and then the derivative with respect to y here, try to highlight it so it's not too lost, is just going to be x. So I'm actually going to put the x just out front. And now moving on to the second piece, we've got y. Then derivative of sine of y is going to be cosine of y. And then derivative of y is 1, so we get sine of y. And then e to the x, y. Okay. So that is one of our mixed partials. And then I'm hoping that this is exactly the same if I switch the order that I differentiate these out. All right, so we're halfway done. Now I still got to find the others, starting with y. So I'm going to recopy the function here, so this way I'm not scrolling all the way up. We've got to take the derivative with respect to y first. And unfortunately here, we've got to do product rule again. So I get the first, and then I'm going to have to times that by the derivative of the second. So that's the partial with respect to y of sine of y. Then I've got to differentiate the first, and we keep the second. Derivative of sine is cosine, so this is e to the xy times cosine of y. And then derivative of e to the xy with respect to y is the same thing back. And then chain rule, I've got to take the derivative of the exponent. And then that sine of y stays attached. So this becomes e to the xy times cosine of y. This is e to the xy. Derivative of that with respect to y is x. And then times sine of y. So now I need to differentiate this with respect to x and with respect to y. So I'm going to start by taking the derivative with respect to x now. Okay. And thankfully, at least for this first piece, just this one is dealing with x. Cosine of y is just going to be a constant. So when I take this partial, we're going to get e to the xy times by the derivative with respect to x of that exponent, and then cosine of y. Over here, sine of y is just treated like a constant. So I have two functions that deal with x. I'll call this my first and this my second. So I'm going to go ahead and just kind of highlight them. These two are getting grouped together. So using my product rule, we have the first, and then I've got to take the derivative of the second. And in that case, the derivative of x sine of y. So I'll add in the extra steps here. Then we've got to differentiate the first, and then that's times the second. So going through these partials, this first one is y. Because we just have an x inside there. Then e to the xy stays put. When I differentiate this with respect to x, derivative of x is 1. So you just get the constant sine of y attached to it. Okay. And then for this next one, when I differentiate e to the xy, we get exactly e to the xy. And then chain rule, I've got to take the derivative of the exponent. And then the x sine of y stays attached. So again, I'm hoping this is the same thing as up here. So far it is looking pretty good, but just to kind of rearrange things and show you, this is y, cosine of y, e to the xy. Put the sine of y in front, e to the xy. And then here, this last derivative is y. So we have y times x times sine of y. So that is x, y, sine of y, e to the x, y. So going through and comparing these, x, y, sine of y, e to the xy. We got that, looking good. This is y cosine of y times e to the xy. That's great, that's that piece. And then sine of y, e to the xy, is exactly this same piece here. So you can see the mixed partials are exactly the same. So we are super close. One last one on this 10-minute problem. Take your time because it's very frustrating if you go through all of this and you find out you made like a tiny mistake back on the first partial. It's kind of gut-wrenching, so make sure you're just being cautious with it. So now we need to go ahead and we need to take the derivative of this with respect to y. And unfortunately, I've got a product rule and I've got a product rule here. So starting with the first one, I'm going to even go ahead and put parentheses around these things. I wish it would stay in the tool instead of keep switching. This is the first product rule. This is the second product rule. So with the first one, we keep the first. And then we're going to differentiate the second. And then we differentiate the first. And we keep the second. Moving on to the second product rule. You can split these however you want, but I'll go ahead and again keep the x sine of y together and the e to the xy together. So we keep the first, differentiate the second, and then differentiate the first, keep the second. Running out of screen room there. So now we got to take these derivatives. So this is e to the xy. Derivative of cosine of y is negative sine of y. So I'm going to pop the minus sign out front. And then here, derivative of e to the xy is e to the xy. Chain rule, derivative of this with respect to y is going to be x. And then we've got the cosine of y attached. Second piece, we've got e to the xy. Derivative of sine of y is positive cosine. So this becomes x cosine of y. And then in the same manner, derivative of e to the xy is e to the xy. Using your chain rule, derivative of that exponent with respect to y is x. And then you have the x sine of y at the end. If you left it here, not a problem. That's no biggie for me. Okay. But just as a notice, in both examples, those mixed partials are equal to each other. So the partial with respect to x then y is the same as y then x. And in this case, we had u, partial with respect to x and y, is the same as y and x. So this is exactly Clairaut's theorem. This should happen when I'm taking a function and differentiating it. Nice functions will have this property. What we're going to have in the future is kind of the reverse of this. We're basically going to be given the partials, and we want to see, can I find a function that has these partial derivatives? Well, if the mixed partials are not the same, it's not going to be a nice function. So we always want this to happen. If it doesn't, it's not something I can work with. Okay. So what Clairaut's theorem states is, suppose that f of xy is defined on a disk which we'll call D, containing the point AB. If these mixed partials are continuous on D, then those mixed partials better be equal to each other at that point, and really all points ending up being in that disk. Okay. So again, this better happen to be a nice function. So really, I just have a couple more examples. If we have functions of more than two variables, if we want to go ahead and find like a third partial derivative, we can find those components. And then the last thing I'm going to do is lead into an idea connecting implicit differentiation, because when we go over chain rule, we'll see another way we can go through that process. So now we can extend the same notation and concepts to functions of more than two variables. as an example, let's find the first partial derivatives. Of the function w, which is a function of three variables, x, y, and z, which is z e to the xyz. So starting with the partial with respect to x. Z is treated like a constant, so that just stays put. Derivative of e to the xy is e to the xy. And then our chain rule tells us we got to take the derivative with respect to x of that exponent. Okay. Well, derivative of x is 1, so these just stay constants attached to it. So this is z e to the xyz, and then we get an extra yz popping out. So if you want to clean this up, you can write yz squared e to the xyz. And then I can continue to take more partial derivatives from here. If I want the partial with respect to y, then same thing. This is treated like a constant, so it stays out front. Derivative of e to the anything is e to the anything. And then chain rule tells us go ahead and differentiate this now with respect to y. And so the derivative of that is going to be xz. The derivative of y is 1. So you get an x, a z, you already had one out front. So this becomes xz squared e to the xyz. And then finally, the last partial, or last first partial, is the derivative with respect to z. So here I'm going to have to do product rule of z times this. So going through that, I keep the first, I differentiate the second, and then I differentiate the first, and I keep the second. Okay. So here, this is z. Derivative with respect to z is, again, the exponential itself. And then chain rule tells us I've got to take the derivative of the exponent. And then here, derivative of z is 1. And then e to the xyz stays put. So derivative of this is just going to be these constants, x and y, attached to it. So this becomes xyz e to the xyz plus 1 e to the xyz. So I think you'd be fine at this point if you then had to find another derivative, because I could take this with respect to y, and then I could take it with respect to z after that. You're going to get a ton of practice with this, but I don't want to make this video 2 hours long for you. So I think this is a pretty good overview of just partial derivatives. So the very last thing I want to do is one example going through implicit differentiation, because it's going to be the same process as before. So if you don't remember, we're going to refresh. So we're going to use implicit differentiation to find the partial of z with respect to y. For the equation e to the z is equal to xyz. So z is ultimately a function of x and y. So remember back in Calc 1, we did stuff like y squared plus xy equals, say, tangent of xy, stuff like this. You went through and you differentiated everything as normal. So derivative of y squared would be 2y. Then here I'd have to apply product rule. The only difference is when I took a derivative involving y, I would always get a y prime attached to it, or that dy dx. Same thing here, you would differentiate it as normal. You'd have to use your chain rule. Anytime you took a derivative of y, you got a y prime attached to it. So now exactly the same thing is going to happen. I'm going to differentiate with respect to y, but my z is going to depend on y. So anytime I differentiate z, it's like I'm getting a z prime attached to it. It's just I can't use the prime notation because it's a partial. Because technically I could do the same thing and I could change this and make it x. Okay? So what I want to do is I want to take the partial with respect to y of both sides. And then anytime we take a derivative of z, we get a partial of z with respect to y attached. Because when we go through chain rule, we're going to see a different way to do this, but this is the process just following the same thing from Calc 1. So this side, I'm going to take the derivative with respect to y. The right-hand side, same thing. Take the derivative with respect to y. I differentiate involving z as normal, so you still get the same thing back. But because I'm taking a derivative of z, I get that z prime, in a sense, attached. It's just a partial. Okay. And now same thing over here. You've got y, and then you also have this z. So it's like I have two functions involving y here. So I really need to use product rule on this. So I'm going to have to take the derivative of the first, which I'm going to keep xy. Second stays put. And then I switch this. Xy stays the same. And then I take the derivative of y with respect to z. Okay. So here we get e to the z, partial of z with respect to y. And then when I take the derivative of this with respect to y, we just get x. Because I don't need a partial of y with respect to y, that's just 1. So this is really x times z. And here we have x times y. Derivative of z is 1. And then again, that chain rule, we get that partial attached. Okay? And your whole goal is to find this partial. So at this point now, I just need to solve for my partial. So I'm going to go ahead and just move this term to the other side. So this is e to the z, partial of z with respect to y, minus xy, partial of z with respect to y, and that equals xc. And then you can skip this step, but factoring out that partial leaves us with e to the z minus xy equals xc. And then dividing through, we finally find what this partial is. So it's xz over e to the z minus xy. So we will see another way to do this very soon in the future, but the same ideas extend naturally.